Good evening and good morning. And today our session will focus on the wind retrieval algorithm, which is the core of our scientific applications. So today's session will be hosted by Professor Chien from National Central University.
Okay, hello everyone. This is Hua speaking. And so we have three speakers today in this session. The first one is myself, and the second one is Dr. Balasubramania from University of Michigan. The third one is Professor Tsai, also from National Central University. Each of us, we will have a talk around 40 minutes. So we have already recorded our presentation. So please, now we can start to broadcast. This is Hua Chien from National Central University, Taiwan, is trying to talk a little bit about the current progress of our team on the combining the new ocean observations for a new wind speed retrieval algorithm. So our team include also one of my PhD student, Zhang Ling, and also a master student, Zhen An, shows the relationship between the NBRCS to the mean square slope, which was considered and adopted in the GNSSR algorithm. So these are basically considered the geometric optics model. And so in this model, we can see that the NBRCS is proportional to the square of the Fresnel coefficient and also as a function of the mean square slope. Factors, they were not taken into considerations in the GMF or algorithm. They become the uncertainty of wind speed retrieval in GNSSR. So how to consider those factors? So there are two approaches mainly. So one could use theoretical analysis to consider these, such as specular point theory, consider the more realistic cases of the microwave electromagnetic wave interact with the ocean surface. And also they can use empirical formulation that obtained from existing airborne scatterometer, altimeter, radiometer, or reflectometer. So such like the topics Poseidon altimeter or train radar, SMOS passive radiometer, or Cygnus reflectometer. So from the figure on your right hand side in the red boxes, so that demonstrate the inverse algorithm. So this is what we have, the GNSSR DDM. From those DDM, we can obtain the observables. And by using these observables like DDMA or LES, these are all calculated from the NBRCS. We use this to build up, to establish the GMF between those observables to the wind speed directly. So that is how we do in the GNSSR algorithm, inverse algorithm. But in this study, what we try to propose is this idea that we separate the GMF that directly link the NBRCS, those observables to the wind speed, into two segments, into two sections. The first one is to establish the relationship between the NBRCS to the mean square slope. And then we can use the relationship between the mean square slope to the wind speed to infer the wind speed. So the advantage of using this strategy is that we can identify and deal with all those uncertainty that occurred in these two different sections independently. Try to demonstrate the feasibility of establishing the GMF between those observables from GNSSR to the mean square slope. So the mean square slope data in this study are mainly coming from those three sources. The first one is the airborne wide swath radar altimeter. It is available from the website. The second is the SMOS satellite from European Space Agency. And the third is the in-situ direct measurements using our own self-developed miniature data buoy. One of the several events we can find the match-up between the airborne WSRA compared to the sickness data. So this is during 2020, during this atomic case. So the average wind speed was only 7 meters per second. So what you can see on the graph, the red dots indicate the locations of WSRA and the blue circle indicate the coverage of sickness. So on your right hand side, the panel, you can see the trajectory of the aircraft. And these are the TC cases. So in the year 2020, in June, so in June 5th and 6th, 2 days, they have 2 flights. What you can see on the right panel, the aircraft start these observations as indicated by these red triangles. So if we match up all those 2 data sets with the criteria that when they locate in the area of 2.5 degree and in time, half an hour, then we collect them all, is what you can see on the left panel. So they co-locate in the same or nearby area in near time, in approximately the same time. So what you can see on the middle part, the first one is the data from sickness, from the sickness MBRCS. And the red color indicate the incident angle. And the rest 3 panels are actually the data from the aircraft. So the first one was measured, the measured mean square slope. And so you can see some gap between each data set. And the second, this one is the significant wave height. The last one is the wind speed. So if we try to match up the observations and build these observable versus the mean square slope, that we can see here on your right panel. So the data are scattered. That's maybe because that the data are not really occurred at the same time at the same location because our criteria is too rough. So in this case, we try to make sure that all these data were measured nearly the same time within 300 seconds, and the range is limited to 0.1 degree. So in this case, you can see when we try to match up this point, as you can see on the left panel, and the data number reduced. So what you can see on the middle part of this slice, that's the observation data. The first one from sickness MBRCS, the second from the aircraft mean square slope, and significant wave height, and also wind speed. So by using this data and the GMF or the relationship between MBRCS to the mean square slope can be seen. And the color here indicate the incident angle. But you can see that the data number is so limited, so you cannot really establish the GMF using this limited number of data. And WSRA during hurricane condition are extremely limited, so we consider to search other possible sources of mean square slope data. So one could find that the SMOS satellite from Europe could provide also mean square slope data in their products. So we try to find the overlap, the match up pairs of the data so that we can compare the mean square slope to the thickness of observables. So here is one example showing that in September 3rd in year 2020, that the red dots indicate the thickness coverage, and the blue lines indicate the SMOS data set. So we find that every day during 8 p.m. to 10 p.m. the local Taiwanese time, and there will be co-located tracks around the East China Sea to South China Sea, which is around the Taiwanese waters. So we use the matchup to compare this SMOS thickness with the thickness observable. What on your left hand side is the LES versus the mean square slope. On your right hand side is the DDMA versus the mean square slope for about 2 weeks, about 16 days in the year between 2018 October to 2020 September. By using this data set, we can try to provide preliminary GMF functions. So this is the first one about the GMF between the DDMA to the mean square slope. So these boxes indicate this 25% and 75% of the cumulative probability in this bin. And the color indicate the incidence angle. So this is for DDMA GMF, this is for LES GMF. Direct measurement of the in-situ wave, mean square slope, and wind, we develop this miniature buoy. So what you can see is the architecture of this buoy. The kernel of this buoy is actually a single chip processor. Is actually a Raspberry Pi, and then it is equipped with a battery power system and also communication system using Iridium satellite, which is able to transmit the near real-time data through satellite to the user. And also this buoy is equipped with the GPS tracking, the GPS sensor, and also the inertial motion unit, which provide this acceleration on 3 axes and also the angle, the inclination angle on both x and y axis. And of course, they are magnetic heading, compass heading could provide the direction. And we have also the temperature and salinity sensors at the bottom of this buoy hull. So how to measure the mean square slope? We actually use the gyro sensor. So in this case, we try to reduce the price of this buoy. So we select the consumer grade gyroscope. And this kind of gyroscope is usually used for the VR glasses, which trying to sense the motion of human motions. So this kind of consumer-grade gyroscope is already equipped with a lot of filter inside the chip, which we don't really know. And so this kind of sensor is actually very small and power saving unit, and it doesn't really equip a rotating gyro. Actually, it uses the Coriolis gyroscope with a very high frequency vibrator. So due to the fact that we're using not industrial components, instead we're using low price consumer grade products, so we don't know if the data quality could satisfy the scientific needs. So in this case, we have to carry out calibrations and validations. We did that in both lab, experiment, and also field tests. So in lab experiments, we carry out these comparison in a giant wave tank in Chengkong University in the southern part of Taiwan. So here you can see that we are deploying a batch of the miniature buoy along in the wave tank. So the wave tank, the length of the wave tank is around 300 meters. The width is 5 meters and the depth is also 5 meters. Actually, it's the second largest wave tank in the world. So could generate a near real wave height. So this is the sketch of the wave tank. And on here you can see the settings of experiment. So we generate both regular and irregular wave with given wave height and wave period. So these are the test cases we did in the lab experiment. And there are two films that showing the case that we were carrying out the experiment. So this orange miniature buoy will align in the middle of the wave tank. On the side, you can see the wave gauges, which use capacity type to measure the elevations. So this is one example of the data that record during the experiment. The first is the pitch data, and pitch roll and then compass heading, and the final one, the bottom, is the vertical accelerations. If we zoom in to see the variation in time series, then the first one is the acceleration. You can identify the asymmetric patterns on the wave crest and wave throw. And the second is the slope. The slope, we take the absolute value of the slope. So the red curve indicate the front slope. The blue means the back slope. And so these are two cases that measured from the experiment. So on the wall of the wave flume, actually we use many wave gauges and trying to use the difference, the gradient of the water elevation to infer the slope. So there are like 3 or 4 wave gauges in a line, so we can take the gradient of the water elevation. So by comparing those slope that obtained from the wave gauges to the miniature buoys, so this is a comparison in temporal domain in different cases, which means in different setup of the experiment, in different frequency, in different amplitude of wave height, and so. So you can also see this room mean square error are quite acceptable. And so by using this data in time series about the slope, so actually they are the Gaussian distribution on 2 dimensions on the x and y coordinate. So if you plot this 2-dimensional Gaussian distribution on this domain, and the color indicated the probability density function. So these are actually the cases that we deploy these drifters, these miniature buoys, at the coastal oceans. So one example, you can see that the shape of this 2-dimensional Gaussian distribution, you can see the elliptical shape, which indicate the wave direction or the wind direction. And you can also identify the major axis and minor axis, which indicate this along wind, this upwind mean square slope, and also crosswind mean square slope. So which are the variants of these slope data. So this is one example that is in time series domain. But actually we are not using this method to infer the mean square slope directly. So on board, so in the miniature buoy, we are actually trying to use the spectrum of the slope to calculate, to estimate the mean square slope in both x and y direction. So these are the equations we use to estimate the mean square slope. And you can see from the integration there is a lower frequency limit to the upper frequency limit. The upper frequency limit is around 10. The wave number is around 10, which is the units radius of meter, considering the size of the buoy is 50 centimeters in diameter. So we compare also in frequency domain. So these figures shows the transfer function between the slope spectrum compared to the slope spectrum that measured by the wave gauges. So here is the response function. You can see that in the middle part, the ratio is approximately to 1. So in this section, these are the data we will try to use for the calculation of mean square slope up to here, up to about 10K wave number to 10 radius per meter. That's the range we take to do integration for mean square slope. So on your right hand side, you can see several cases of the real measurement. So after smoothing, this is the blue curve after smoothing of the spectrum, and this dashed line are the upper limit we do for integration, which is about 10 radius per meter in terms of wave number. Validation that we carry out in coastal oceans. In the left panel, you can see a satellite image on which you can see the location of wind anemometer and also the location of miniature buoy. So we separate the wind direction into onshore wind and offshore wind according to the white line, as you see, because the miniature buoy was located in the bay. So on your right hand side, that shows the comparisons of the data to the wind speed. So the wind speed data, what you can see on the vertical axis on your left hand side in blue color indicate the wind speed that measured by the anemometer. And on your right hand side, the axis in green color indicate the parameters measured by the miniature wave buoy. So the first panel shows the wave height. Of course, the wind speed correlate with the wave height. The second is the steepness of the wave in black dot. And the third is the mean square slope that was estimated using the above-mentioned spectral methods and then compared with the wind speed. So it seems that the wind speed and mean square slope has very high correlation. So these two are the figures showing the dependency of mean square slope with wind speed in the in-situ calibration experiment at coastal zone. On the left-hand panel, that is the data showing all the cases of wind direction. On your right-hand side, that only shows you the cases when the condition is onshore wind. So both these panels in coastal oceans, you can see that a very high correlation coefficient could be obtained by using the linear regression as the red solid line. And the other dashed line or blue line indicated the empirical formulation obtained from literatures, such like this is from Cox and Monk, and this blue curve that was proposed by Jin Wu in 1990. So there is a offset between the level that is due to the range of integration is different. We only has the integration from 0.05 to 0.17 in frequency, so that's called a low pass mean square slope, but still you can see the relationship. So that figure demonstrates the feasibility of using this kind of miniature buoy for detect this mean square slope in coastal oceans. So we extend our experiment offshore, not only in coastal zone, but all the way to the continental shelf. So in this figure, this was the experiment we carried out in 2020, last summer, during the passage of typhoon. So on the left-hand side, the color in this figure indicate the water depth. That's on the continental shelf. So we deploy around 40 miniature buoys at the northern coast on the East China Sea. So the black dot indicate those drifters, those miniature buoys are not moored. So they drifted all the way with the current. And the red dots indicate these miniature buoy, they are attached to a nylon cable which is moored, so they stay in the same location. So we have time for discussions. So anyone would like to propose comments or questions? Okay, so if there is no further questions, I will close this session. And so thank you everyone for joining this meeting today.